what's the connection between energy and chemical reactions. That was the first thing. And then what's the connection between those chemical reactions and gases as either a reactant or product. So I wanted to connect them to sort of, hopefully be a good way to sort of think about both of those things going into the test on Thursday. Because, what really the whole point of like doing any of this chemistry is to try and see how everything's interconnected. Because when you see how things are connected, they make, hopefully, well, to me anyway, things make more sense. If you are learning things in isolation, I can't remember things that I learned in isolation. What I do remember is like when something connects to another thing that I know, and then you see they're connected, that I remember them, and they make more sense. So in each of these questions, sort of put together ways to calculate the amount of enthalpy or energy for different reactions, endothermic and exothermic, using Hess's law to break down a reaction into components that we can measure, and to try and remember fundamental concepts like enthalpy of formation. What does that mean? How can we use that in terms of figuring out energy and Hess's law? And I think the last question kind of puts it all together in, can you remember more than one way to calculate these energies? I think that'll be like the last one we do before we go. So a lot of these are similar. They sort of ask you to calculate an enthalpy and then use that information to go on and calculate something about one of the reactants or one of the products. So is there a particular one you wanted to start with, or anybody have any questions about how to get started with any of these problems? Is there one you'd like to begin with?
I'm just sidebarring. Did we skip recitation 11? Or
this is recitation 11.
Oh, because the email I got said recitation 12.
Oh, I probably just screwed that up.
Oh, okay. Yeah, I was confused. I was like, oh, I just want to make sure I'm doing the right one.
I think that's just on me.
Okay.
No, this is 11. Yeah.
Okay. Yeah, I just wanted to make sure.
Right. Get my. Anyway, is there one in particular you guys wanted to do or start with? We can do a couple of them together.
Maybe number 3.
Okay. Remember, whoever speaks first gets heard. So people want to come back to this one, we can. But anyway, yeah, number 3. So this is 1. This is 2. This is 3. Okay. Yeah, so like I said, these questions are going to are sort of forcing you to remember concepts. And so this question, we need to calculate the enthalpy of the formation of methane. And there's I've given the reactions we need to calculate in red. So that's the target we're going for. Now we have to remember delta H combustion. What does that mean? Someone give me a native. What does that mean, delta H combustion?
Like is it the heat that is released?
From what?
Like from the reaction?
What reaction? Yes, it is heat released from a reaction, but what reaction are we talking about?
Combustion reaction. Is it combustion?
Mm-hmm. What's a combustion reaction?
Is it exothermic reaction?
There's a lot of different exothermic reactions that aren't combustion reactions. It's a particular kind of exothermic reaction. So everybody's slightly right, but there's like one thing that, yes, it's an exothermic reaction. It releases energy. What specifically takes place in a combustion reaction?
Like when it reacts with oxygen and like burning something.
Burning with oxygen.
Yes, exactly. It's a rapid, basically it's a super rapid oxidation of something, like with burning and heat involved. And so the combustion of oxygen, how would we write out a formula, chemical formula or reaction formula for the combustion of carbon? What would that look like? We had, so here's a reaction for the formation of methane. So that's our chemical formula for what's the chemical formula for the combustion of carbon? So your carbon is a solid. And what are we reacting it with? Ooh, that was fun. Sort of lost the internet here for a minute. Go back. Okay. Did everyone hear me again? Because hello?
Yeah.
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 Yeah, sorry about that. I don't know what happened. All right, so 1, 3. So before we so rudely interrupt, how do we write chemical reaction for the combustion of carbon?
CH plus O2.
Mm-hmm. What does it give us?
CO2 and H2O.
Where do we get the H2O from?
Or ooh.
From where?
I don't think we need a water because we're not working with aqueous solutions.
There's no hydrogen. So it's not,
Yeah.
it's not that it's aqueous. There's no hydrogen. So we've just got C plus O2 gives us CO2. That's our reaction. That's the combustion for carbon. Combustion for hydrogen. How would we write that? So if the combustion of carbon is C plus O2, what's the combustion of hydrogen?
Would it be hydrogen plus O2?
What's hydrogen though? What's the chemical formula for hydrogen?
H2.
Mm-hmm. So H2 plus O2 gives you what? Product.
2H2O.
2H2O. Interesting. So is that a balanced reaction?
No, you need to put a 2 for H2.
I need 4 there?
2 for H2.
2. Yeah. Right. So methane, what's our combustion for methane? Oh man,
Plus
thank you. So what is it?
wait, CH4 plus
Mm-hmm.
O2
CH4 plus O2. What is
um,
that? What are our products?
CO2 and H2O.
Yeah. However, not balanced, right? Because we have 3 oxygens on the right side and only 2 on the left. So what are we going to do?
Multiply O2 by wait, can you, because you have 4 hydrogen on the left side. So
Mhm.
can you multiply H2O by 2
We can.
and then multiply O2 by 2 to get 4 oxygen.
That's right. So 1 mole of methane, 2 moles of oxygen give us 1 mole of CO2 and 2 moles of water. So those are the 3 reactions we have. We need to arrange these in a way that we get back this at the end. So if you remember, when we do these sort of this, so this is classic Hess's law question. And when you do these, first thing I like to do is find out where are my reactants, where are my products, get them on the right side. So where are we going to find C? So carbon is a solid. Where are we going to find that? Reaction 1, 2, or 3?
Reaction 1.
Mm-hmm. So do we need to do anything to reaction 1?
No.
Yeah, because it has 1 mole of carbon on the left side as a reactant, so won't do anything with that one right away. What about our hydrogen?
No as well. We don't need to change it because it's already on the right side. Or I mean, it's on the products. No, the reactant side.
There you go. Yeah, we have hydrogen on the reactant side in number 2. So don't have to worry about that one. And what about number 3?
We need to switch it or switch the sides.
Yeah, what we need to put, why do we need to switch it?
Because we need to get the methane on the reactant side to the product side.
Right, so we need to switch that last one. Let's do that. Let's switch it around. So I'll write it out flipped. So when
And the energy too is also becoming positive for the third reaction.
right, so when I flip it, it's gonna be 2H2, 2 waters, and plus H2 plus C2 gives us CH4 plus 2 waters. Right? No, plus O2, 2 O2s. There we go. Right. So so the energy associated with that will now be positive. So that will be plus 891. I also want to point out that the combustion reaction we did for hydrogen is, I mean, that is correct, but we have to take into account the fact that we burned 2 moles of hydrogen. And so the combustion for hydrogen that is given here is for 1 mole of hydrogen. Because remember, anytime you put delta H in front of something, it means per mole, right? So the combustion of hydrogen would be per mole of H2. And
So the negative, oh, sorry.
so we need to double that. Yeah. So this
Okay.
would be minus 484. And the first one, what's their energy associated with the first one?
First reaction, we didn't do anything, so it stays the same.
Right, so it's the same, minus 394. All right, so let's see if we can balance these reactions. So we've got, first thing I see is we got water on both sides. So I've got 2 moles of water here as a reactant, and I've got 2 moles of water here as a product. So that is an intermediate. So it is produced, then it's consumed. So it's like it was never there. So that is gone. Next.
2 moles of oxygen also cancels out
So we got 2 moles of oxygen here.
on the product side, and
As a
then
product.
we have 2 moles of oxygen combined with the reaction 1 and 2.
Right. So remember, you're adding all of them. That's right. You're adding all of them together, not just, so if there's 1 mole of oxygen in 1 and there's 1 mole of oxygen in 2, that's a total of 2. So we're going to add these 2 together. So it's 2 moles of oxygen as reactants, and that's 2 moles of oxygen as products. So they're gone. What else can we eliminate?
Like carbon dioxide.
So where are my carbon dioxides?
Reaction 1 and the newly changed reaction 3.
Right. Since we flipped reaction 3, CO2 is now a reactant rather than a product. So we can see from here, CO2 is a product from oxidizing oxygen, oxidizing carbon, or burning carbon, combusting carbon. And when we basically reverse the combustion of methane, we're forming methane, and we're forming it from water and CO2, so now it's gone on both sides. So it's a reactant and it's a product. It's also an intermediate. So what I left is C plus 2H2 as my 2 reactants. My only product that's left is CH4. So that is the balanced reaction we wanted in the first place. So that is the same as this reaction up here. That's the formation of methane. So that's the formation of 1 mole of methane. That's why it's a delta H. We're forming 1 mole of methane. So what's the overall enthalpy for this reaction?
$13.
Remember, 13 what? 13 is not
Oh,
a,
sorry, kilojoule.
there you go. 13 kilojoules plus, so it's positive 13 kilojoules. And generally the energy of formation is going to be positive. Sometimes it's not. If you're forming CO2, for instance, and we'll learn later when we do a little later we're going to do oxidation and reduction. And we kind of did oxidation numbers. Remember we did oxidation numbers? When you're forming something that's reduced and carbon is reduced here, carbon goes from an oxidation number of 0 when it's just carbon by itself. And then when carbon's in methane, it now has an oxidation number of -4. And usually when you reduce something, that takes energy for it to happen. When you oxidize something, like when you burn something, that releases energy. So in this instance, it costs 13 kilojoules of energy to make 1 mole of CH4. So then you use that information to go to the next screen, the next question. And you use that information that we just figured out. So what was the information we just calculated? So we calculated that our delta H formation was 13 kilojoules. So we used that information to figure out what amount of gas is produced. So in this instance, 500 kilojoules of energy is absorbed in this reaction as we made methane. How much methane did we make if the temperature is 100 degrees and the pressure is 10 atmospheres? So how do we start doing this question? What's the first question? What's the first thing we need to calculate in order to do this problem? We need to start somewhere. So we know it's a gas law problem. So it's going to be Pivnert at some point, right?
We need to, I guess the easiest thing to do first is probably list out our variables that's already given to us.
nRT. It's a little wide. Right. So we need to figure out what we have. So our pressure is 10 atmospheres. So we know that. And our temperature is 100 degrees.
Would you convert the
You
100 to
kelvins, right? By adding
Yeah.
273.
Uh-huh.
This.
Yes.
I don't know.
Yeah. Yes,
Okay.
we do.
So we have to basically use.
Hello? Is that the other meeting going on? So we add 273.15 to that. So our temperature is 373.15 Kelvin. So we've got pressure, we've got temperature, we know what R is. We're asked for volume. Oh, we need N. How are we going to figure out N? What's N? What is N anyway? What does it stand for?
mole?
Number of moles. That's why it's N. So how do we calculate the number of moles? So remember, we needed to use the answer from the last problem in this one. So the answer we got from the last problem is this. How are we going to use that information to calculate the number of moles of gas?
Don't we refer to the don't we just refer back to the balance equation then? Because you can you just do like a problem saying like 500 kilojoules times 1 mole of methane over 13 kilojoules? So therefore it's saying like, that should be like the one, it should be referring to the ratio.
That's right. I mean, so you intuited very correctly that since the delta HF is the formation of 1 mole, and that's why it's delta H, because it's 1 mole, forms 1 mole of methane. If 1 mole requires 13 kilojoules of energy, then if we have a reaction that required 500 kilojoules of energy, it must be more than 1 mole, right? And so you use the ratio of kilojoules per mole to your advantage to figure out how much it is. So our kilojoules cancel and we're left with moles. So if 13 kilojoules makes 1 mole, how many moles does 500 kilojoules make?
I got 38.46.
Okay. 38.46.
Can someone verify that? I just want to make sure if I got the correction right, because it's just 500 divided by 13, right?
Mm-hmm.
Okay.
Yeah, I used 38.5, but yeah, 38.46 is the right, yeah. Mm-hmm. So now we have all the information we need, right? Because we know what N is, we know what R is, we know what T is, we know what P is, and we're asked to calculate volume. So now we just have, now volume is going to equal nRT divided by P. And remember, R is 0.0821 atmosphere liters per mole Kelvin. Let me set all that up. Let me just erase this. So I put in my number of moles, 38.5 moles. Multiply that by 0.021.
Oh, just out of
Mhm.
curiosity.
Yep.
So when we input our temperature, should we input the 0.15
It's fine.
or okay?
Just remember to round back when you give your final answer.
Okay.
And then divide all that by 10 atmospheres. So I've got moles as a denominator, moles as a numerator. I've got liters by itself. I've got atmospheres down below. I've got atmospheres up top. I've got Kelvin as a denominator and Kelvin as a numerator. So basically, I'm left with liters, which is what I want because volume should be in liters. So how many liters? What's my answer? How many liters do I get? So it's 38.5 times 0.821 times 373.15, and then divide the whole thing by 10.
I got 117.82.
Okay.
Yeah, I got the same thing.
117.82 what?
Liters.
There you go. Is that your final answer?
Yeah.
Don't we have
Wait.
to round?
Mm-hmm. You'd lose some points because you have too many significant digits there. So how many
Just to round it to 118.
I would say probably to second, right? Or
Actually,
second. Or
actually,
second.
actually 500 kilojoules of energy only has one significant digit. That's a mistake on me. It should be 500 period kilojoules. Because, and the number of, in our formation should be 13.0 because there was information past the decimal point. So yeah, 3. There should be 3 significant digits, but I made a mistake here because there's only 1. So
Yeah, I got confused because I just thought maybe it would be 2 significant digits because of the 10 and the 13.
10 atmospheres has 3 significant digits. Yeah, the 13 only had 2, but we should have reported that number as 13.0 because we did have information beyond the 0. I think we did. Oh no, we didn't actually. Yeah, so 2. So 120 actually would be the if I reported the heat from the last as with a 0.0 at the end of it, then we would be fine with 0.0, but I didn't. So yeah, so on the test, I will make sure to put those in. But yeah, you're right. So it would be 2. So the correct answer would be 120. But yeah, also would have accepted 118. 117.82 is too many, definitely. So yeah, so you use the information from the last problem to inform this problem. And the same thing is true. I can just basically just want to show you the introduction for the next one because there's a couple of things going on that you may not be familiar with. So let's look at number 5. I'm not going to go all the way through, but I just want to get you started. Because here again, there's some things you have to do before you even start the question. So the standard, that's asking for the standard enthalpy for the formation of acetaldehyde. And acetaldehyde is CH3CHO. And so the first thing we need to do is, we don't know what is the formula for the formation of acetaldehyde. That's our target reaction, and it's not given here. So anyone help me out? How are we going to, what does that mean when it's the standard formation of acetaldehyde? Anyone remember what that means? I mean, we know that so at the end of it, we should get CH3CHO gas. But what's on the other side? What are we making it from? So this is our,
So when it says,
what are the reactants? Mm-hmm.
When it says the formation of the formaldehyde,
Acetaldehyde. Mm-hmm.
oh sorry, acetaldehyde,
Mm-hmm.
is like asking for like the actual like chemical like I guess equation of how to make it?
Mm-hmm.
Oh, okay, and then
But what are we making it out of? That's the key. When we're dealing with the enthalpy of formation, we're dealing with a very specific set of reactants. So we know that there's got to be, it's got carbon, it's got hydrogen, it's got oxygen. So where's the carbon, hydrogen, and oxygen going to come from for a standard enthalpy of formation, for standard formation reaction? Where do all the reactants come from? I have to go back into the hazy past from like, a whole chapter ago. What are my reactants? I need 3. I need carbon, I need oxygen, I need hydrogen. So the question is, what form? It's something, here's a sort of, hopefully this will be a bit of a reminder. Can anyone remind me for the standard formation, what does that mean? It's standard. So it's standard conditions. What does that mean? What are standard conditions for a chemical reaction? Oh man, forgot a lot of this stuff already. What's the temperature? What's the pressure then?
Wait, are we talking about STP?
STP. Mm-hmm.
22.4 liters and then 1.
No, standard temperature and pressure, not volume.
Oh wait, 273 kelvins and then 1.00 atmosphere.
Right, 1 atmosphere. And when we're dealing with XC, we were dealing with standard of formation. We're usually talking about 25 degrees. So 25 degrees C in 1 atmosphere. So if those conditions, I need carbon, I need oxygen, and I need hydrogen. In what form am I going to get those 3 things? What form is carbon at 25 degrees C in 1 atmosphere? Solid, liquid, or gas?
A solid?
Solid. It's graphite. That's basically what the standard at STP, it's standard conditions for the formations, for the standard formation of anything. It means, what that means is that you need to get all of the atoms in that molecule from the lowest energy, the most stable form of those atoms at 25 degrees C and at 1 atmosphere. And so the most stable form of carbon at 25 degrees C in 1 atmosphere is graphite. So carbon, solid. So I got my carbon. Where's my hydrogen? Where's my hydrogen at? How am I going to get my hydrogen at? Internet connection's unstable. Again. So where do I get my hydrogen from? What's the most stable form of hydrogen at 25 degrees C in 1 atmosphere?
A gas?
Mm-hmm. What form?
H2.
H2, exactly. So I need H2 gas. What about oxygen? What's the most stable form of oxygen at 25 C in 1 atmosphere?
O2.
O2, right. So I've got carbon, solid, hydrogen, gas, H2, and oxygen, O2, gas, makes my acetaldehyde. Now I need to balance it. I need to balance all my reactants so that I make 1 mole and 1 mole only of acetaldehyde. So my carbon, how many moles of carbon am I going to need?
2.
2. Yeah, so there's 2 moles of carbon there. So I need 2 of them. What about my hydrogen?
2 moles.
2. Mm-hmm. And what about my oxygen?
Half.
1/2. Mm-hmm. So this is our target reaction. 2C plus 2H2 plus 1/2 O2 makes CH3CHO. That is what we're going for. We need to balance the rest of these reactions to get that, okay? So, A, balance the combustion reaction. So the combustion reaction is acetaldehyde plus oxygen gives you water and CO2. That's what happens when you burn hydrocarbons. So this one's got hydrogen, carbon, and oxygen in it. So when we burn it, we make water and CO2. So I gave you a little help with this one because this one's a little tricky. So it takes 2 moles of acetaldehyde. So we need to balance this reaction. So I got 2 CH3 CHO plus O2 makes H2O and CO2. And so since oxygen is in both carbon and water, it'd probably be best to balance like the carbon first. So how many CO2s are we going to make? How many moles of CO2 are we going to form to balance carbons on both sides?
We would need 2 moles of carbon on the reactant side. Wait, did you say CO2 or
CO2, how many moles of CO2 are we going to make from this reaction? Excuse me. How many moles of carbon do we have as reactants?
Are you referring back to the formation of the?
Nope, I'm talking. It's just right now we're just doing the combustion reaction. So
Okay.
is balance the combustion reaction. And this is the combustion reaction here. It's not balanced. And I helped you out by putting the 2 there. That was a hint. So how many moles of carbon do I have on the left side? How many moles of carbon as reactants are going into the reaction? Moles of carbon atoms.
Is it 4?
It is 4. Yeah. There's 2 moles. Remember, there's 2 moles of carbon atoms in acetaldehyde. There's 1 here. There's 1 here. And we're burning 2 of them. So that means there's 4 moles of carbon. So how are we going to get 4 moles of carbon as products?
You multiply CO2 by 4.
Right. Now, I want to balance my hydrogens. Basically, whenever you're doing a combustion reaction, you generally balance the carbons first, the hydrogens second, and then leave the oxygens for last, because oxygens go in both. So that makes oxygens a little bit tricky. But if you've got the carbons down and the hydrogens down, then the oxygens should follow. So we do carbons first, now we do hydrogens next. How many moles of hydrogen do we have on the left side as reactants? How many moles of hydrogen atoms? 8. Yeah, there's 3 here. And there's 1 there for a total of 4. And we got 2 molecules, so that's 8 moles of hydrogen atoms. So how do we balance that with as products? How do we balance the hydrogen as products?
You multiply the H2O by 4.
Mm-hmm. Now I've got 8 hydrogens over here, and I've got 8 hydrogens over here. So they balance. So my carbons balance, my hydrogens balance. I only got oxygens left. So how many moles of oxygen do I have as products?
12.
Oxygen atoms.
12?
12, right. Yeah, there's 4 here. And there's 8 here for a total of 12. 12 oxygen atoms. Remember, when you're dealing with balancing equations, it's atoms, not molecules, because the number of atoms on one side has to equal the number of atoms on the other side. Number of molecules can be completely different, but the atoms have to add up. So I've got 12 on this side, and I need to put 12 as reactants. So how am I going to do that?
You multiply O2 by 5.
It only gives me 10 though, right?
You already have oxygen on the acetaldehyde on like the reactant. Like
Ah, you did not fall into my trap. Nice one. Yes, 5. Because yeah, we've got 2 over here, 2 oxygens here, and we've got 10 oxygens here. So for a total of 12. So now everything's balanced. So our combustion reaction is 2 acetaldehydes plus 5 oxygens give us 4 waters and 4 CO2s. So then basically now it's just a Hess's law question. So we use this reaction. So this would be our reaction A. Formation of water will be reaction B. And formation of CO2 will be reaction C. And you use A, B, and C, and you try and come up with, this is our target. 2C plus 2H2 plus half a mole of O2 gives this, gives you your product. And then you just calculate delta H. Okay? So I'm not going to do that because you guys should know how to do that, hopefully. But I was worried that you wouldn't know how to get to the target because you may not have remembered what standard formation is. And you can see here the standard formation of water. It's the formation of 1 mole of water. So it's 1 mole of hydrogen and half a mole of oxygen, because you have to form 1 mole. The same with CO2. It's whatever the most, what's the most stable form of carbon and stable form of oxygen. And so it's just C plus O2. So let's take those 3 reactions, figure out what heat is, what's the change in heat during this reaction of making this reaction right here. If heat is released or heat is consumed, one or the other. And I'll give you a hint. It should be an exothermic reaction, because you can tell the next question says if 300 kilojoules of energy were released. Well, that's kind of a giveaway. So you should get a negative number. When you finish this, you should get a negative number, exothermic. And just like we did with the last question, you've got a delta H, which means per mole. So then you figure out how many moles of gas you have. And then based on now that you have moles, you have the number N. You know what R is. It's giving you temperature and volume, and then this time you figure out the pressure. We figured out volume last time. This time we figure out pressure. Okay? So I wanted to go over just the last part of the last question, because it's an important thing to remember before we go. But before we go to that, any questions on how to do this particular problem? It's like any of these problems, figure out what the target is. What's the target reaction? I need to know what I'm going for at the end. If it's a combustion reaction, I need to know what that is. I need to know it's plus oxygen, and I need to know what the products are. And I need to balance it. And if it's a formation reaction, standard formation reaction, I need to know that that's all of my reactants, the most stable form of the atoms that go into that molecule. If it's hydrogen or oxygen, it's going to be H2 and O2 as gases. If it's carbon, it's going to be a solid. And it's always just the atoms, C plus H plus O. Or if it's nitrogen, it'd be N2. But it's all just each one of the atoms separately. Now, any questions about how to do this particular problem? Oh. Yes, there's a motorcycle on our street, and we're now aware of it. So, hopefully they'll go leave in a minute. So, yeah, just a matter of figuring out what the reactions are, balancing them, and then doing your magic with Hess's law. You should get an exothermic reaction out of this net after you've swapped everything and multiplied and divided, whatever else you need to do. So any questions about this one before I go to the last question?
So just out of curiosity,
Okay.
will we ever need to? So on the exam, are we going to be doing like a similar problem like this, where we have to use STP to find our target equation?
If it's a standard enthalpy of formation, yes, you have to know what the standard temperature and pressures are. But really, what does that mean? Basically, that just means that at that standard temperature and pressure, oxygen's going to be a gas, hydrogen's going to be a gas, nitrogen's going to be a gas, carbon's going to be a solid, and that's pretty much it. You just need to know what forms each of them are in, because you will find with some of these Hess's law questions, you may have to change the state of something. Like for instance, water may be produced as a liquid in one reaction, but then it's consumed as a gas in another. That means that you have to add energy in there to change it from a liquid to a gas. And that's another reaction. So you have to add that in. So that's
Okay.
it's important to have the state of each one. You can't just have carbon plus oxygen gives CO2. It's got to be a solid, it's got to be a gas. Okay? I may, since I'm mean, I may include one of those. Change of state in there. It'll be your fault. Now I'm going to add that to one of my questions.
Nice.
Yeah, you're welcome. All right, so let's go to the last one. Because, oh, don't cry. Save it for Thursday. Right, so this is just basically another Hess's law question. So like, yeah, man, should be able to do this in our sleep. But I want you to use two different methods. And I'm going to show you one of them. The other one you should know. So you got three reactions, and you're trying to put them together in some way to come up with a fourth. So we need to write out what the fourth one is, because it's just given in words, described. So the reaction is acetylene, C2H4, with fluorine gas to make, what's CF4? What would we call that? What would be the name of CF4?
Carbon tetrafluoride.
You got it. Nice one. Carbon tetrafluoride and HF. So here's our reaction. So C2H4 plus F2 gives us CF4 and HF. So we need, first thing, what do we need to do first? What's the very first thing we need to do? Guess the very first thing. We've sort of written down the equation. What do we need to do next?
Balance the equation.
Yeah, got to balance it. So first thing to do, probably, since we've got carbon, we got fluorine in two places and carbon in one, probably balance the carbon first, I imagine. So let's balance the carbon first. So how many carbons do we have as reactants? How many atoms of carbon are on the reactant side?
2.
2. And so how many do we have to have on the product side?
2.
2. So how am I going to do that?
Multiply CF4 by 2.
Mm-hmm. Right. Balances my carbon. Next, I want to balance my hydrogens. So many hydrogens do I have? How many hydrogen atoms in the as reactants?
4.
Mm-hmm. So how am I going to balance it on the as products?
Multiply HF by 4.
Mm-hmm. So far, so good. Oh man, that stinks. All right. Plus 4 back. 4 HF. It's terrible. Okay, so I've got 2 CF4s and 4 HF. Man, I don't know why I can't draw on this thing today. Erase all of this nonsense. Try it again. All right. Plus 4 HF. There we go. So I got my carbons balanced. I got my hydrogens balanced. I need to balance my fluorine next. How am I going to balance my fluorine?
Multiply F2 by 6. Because you have 12 on the product side.
I got 12?
Yeah. Wait.
I got 6, don't I?
Wait. So you have F4.
Oh, F4, duh. Sorry. You're absolutely right. I screwed that one up. Yeah, so there's 4 and 8, 12. Yeah, so 6 moles of fluorine. So this is my target reaction. I need to know what delta H is for this reaction. And like I said, there are 2 different ways to do it. One, I'm sure you remember. One is just to take these 3 reactions that you're given and mix and match and multiply them and divide them and flip them around and do whatever you have to do. But there is another way to do it. Anyone remember the other method? I take it that nobody remembers the other method. You remember there's, we go way back into the before time. Anyone remember seeing this sign? I'm not making it particularly well. The summation sign. Anyone remember seeing that?
That's on the recitation number A, I think.
Could be. So where did that come in? What did we use it for? Do you remember?
Wait, the symbol?
Yeah, so this symbol means summation, right? What would we sum in order to get, so if I want the delta H for a reaction, what could I sum to get there? I need to sum something. Anyone remember what it was I would sum together? I'd add something together. Give you a hint. So I would sum together something about the products. I take all the products and I would subtract summation of something about the reactants. What is it about the products and reactants I'd be summing up?
Delta A. Wait. No. Mm,
So when you do a chemical reaction, you're breaking something and you're forming something else, right? So when we do this reaction right here, what you're actually doing in this reaction is you are breaking this and this. You're breaking down the reactants and you're forming these. You're forming these products. So what is it? What values for products and reactants could I substitute in order to come up with an enthalpy for the overall reaction? Remember, I want delta H for the whole thing. What delta H's could I put in there? It's sort of like, it's just like Hess's law. If I'm forming something, I'm creating something else, I'm breaking something else down, I'm flipping equations around. So what values of delta H could I put in there? Since I'm forming reactants and I'm forming products, I'm breaking down reactants. If I'm forming products, what delta H for forming products would I want?
Would you take the delta H of reaction 1 and multiply that by 4?
What is it though? What is number 1? What is that reaction?
That's the formation for the, or like, yeah, that's the formation for,
For HF, right?
yeah.
So the delta H for that would actually be delta H formation of HF. Oh, man, I cannot draw on this today. That is the delta H formation of HF. Number 2 is the delta H formation of CH4. Number 3 is the delta H formation of C2H4. So what I want you to remember is what we can do is take all of the heats of formation of the products and add them together because we're forming products. So all the heats of formation of the product, we just add them all together. Now, as far as the heat of formation of the reactants go, we need to subtract those because we're actually doing the opposite of forming reactants. We're breaking them. So instead of going forwards to formation, we're going backwards to breaking them up. And so we have to subtract those. So we sum all the heats of formation of our products and we subtract all the heats of formation of reactants since we're doing the opposite of formation, subtract them. So to get this, just like you suggested, we would take 4 times the heat of formation of HF. Since we're making 4 of them, so we got to multiply it by 4. And we would add to that 2 times the heat of formation of CF4. So we add these two together and we subtract the heat of formation of C2H4, which is this up here. So 2 times minus 2 times the heat of formation of C2H4 minus, oh, plus, sorry, the heat of formation of F2 times 6. Now, what's the heat of formation of F2? That's the other thing you need to remember. What's the heat of formation of fluorine, F2?
0.
0. Very good. Yeah, the heat of formation of any, the most stable form of that atom is 0. So the heat of formation for F2 is 0. The heat of formation of F is something else, because that's not the most stable form. Like the most stable form of oxygen is O2. It takes energy to form either O by itself or ozone, O3. Both of those things take energy to form because they're not the most stable form. So the most stable form is F2, H2, O2, N2. So this is 0. So we don't actually need that. That's going to be 0. So one way to calculate this is to take 4 times the heat of formation of, excuse me, of HF, which is here. That's the heat of formation of HF. 2 times the heat of formation of CF4, and that's this. And then we subtract from that 2 times the heat of formation of C2H4, which is this one.
That would help us find our delta H for
this reaction right here. All those together gives you the overall heat of reaction for this one right here. Where you,
but isn't our F, we don't know our F delta H though.
just talked about that. What's our F2 is the most stable form of that atom at standard temperature and pressure. So the heat of formation of making the most stable form of any atom at STP is 0.
Okay.
Formation of graphite is 0 because that's the most stable form of carbon. Most stable form of hydrogen is H2, so that's 0. O2, 0. H2O, that's not the most stable form of H or O, and it's not an atom. It's 2 different ones. So the most stable form of any atom at standard temperature and pressure, it's 0. That's how much energy it takes to make that. So I'll give you the answer you should get is, whoops. Well, stable, once you've figured it out, it should be minus 2382 joules.
That's a rounded number, right?
Kilojoules, sorry. Yeah, actually it should be 3. It should be like 2380 kilojoules minus. And then when you do it the other way, when you use Hess's law, you should get exactly the same answer. That's the whole key to this question. If you have heats of formation for everything, you don't need Hess's law. You can just go right ahead and calculate it. But if you don't have the heats of formation of everything, then you need to use Hess's law to figure out what the overall heat of the reaction is. But if you have all the heats of formation, just go right ahead and just add them up much, much faster. But in both instances, you need a balanced equation. So we needed to balance this overall equation. And yeah, so, oh, wait a minute, it's 1 mole of C2H4, right? So just 1.
Yeah, I was wondering why.
1 mole of C2H4, sorry, just 1. That should give you 2380 kilojoules.